Nice to meet you all and welcome. My name is Scott Newman. I'm Senior Vice President of Life Sciences at Meaningful Insights Biotech Analytics, or MEBA for short. I oversee the data team and I'm joined by my colleague, Zach Liu. Go ahead, Zach.
Hi, I'm Zach Liu. I'm a senior principal scientist in MEBA. Great experience to working in the team to deliver. Yeah, it will be nice to go over the slides and take your questions later.
So today we're going to talk about an AI-enhanced oncology data model and how we've used it to unlock insights from electronic health records using natural language processing and large language models. Quick disclosure, Zach and I work for Meaningful Insights Biotech Analysis, as we've already mentioned. So here's the structure of the talk. Brief introduction. We're going to talk about our NLP pipeline development. Zach's going to provide some technical details, some color around the more general topics that I introduce. We'll talk about our enhanced data model and then how we use it to match community oncology patients to clinical trials. Finally, we'll talk about a newer approach where we've devised a hybrid NLP large language model to find adverse events. Then we'll wrap it up with a summary and a brief discussion. So let's get on to the main content. The challenges of working with real-world oncology data. So as we all probably know, oncology is a very complicated space. About 85% of cancer patients are treated in the community, so small centers close to their houses, and MEBA partners with community oncology networks and biopharma to gain meaningful insights from that data. But what does that actually mean and why is it complex? So a lot of these electronic health record systems have structured data, diagnosis, staging, medications, etc. But we all know there's a whole lot of data inside of MD notes and documents and scans. And until quite recently, the only option has been to laboriously and manually go through all of these notes to extract the useful information that you want to know. At the scale we are operating at, several hundred thousands of patients, manual review and abstraction is just unfeasible. So Zach and I have been busy building automated approaches in order to unlock insights from unstructured data. And here's just a little visualization of some of the work on our team. It's the journey of a single prostate cancer patient. On the right in green, you can see data that's available from structured fields in the EMR system. And on the left, we have a load of additional information 4 years prior to them showing up at one of our clinics. Diagnosis date, how their prostate-specific antigen scores move over time, initial lines of therapy. And so without going into the notes, all of this would be missed and we'd end up with an incomplete patient journey. And if we're in the business of generating accurate and timely insights, of course, we need a complete patient journey. So here's just a quick schematic of the data machine that we built at MEBA. We pull nightly from a number of different systems from our partner networks, including structured and unstructured data from the electronic medical record, pharmacy data, genomic testing data, claims data, imaging diagnostics, etc. We run a series of pipelines to extract all of the useful information and structure it in a consumable format in which we can gain actionable insights that we feed back to sponsors and to the network. So that was the introduction, but now let's move on to our natural language processing pipeline that we developed to enrich oncology patient data. And at this point, I'll hand it over to Zach to talk about more of the technical details.
Yeah, for the information extraction, we deployed the John Snow Labs NLP pipeline. You can see here, we start from the medical records. Some of them are PDFs, scans. Some of them are just raw note text. And for those PDFs, we need OCR. John Snow OCR is one of the package we use, and we also use John Snow Clinical NLP and John Snow A-Lab for annotation, and John Snow Lab the demo notebooks to start build our pipelines I will mention below. And from either from the PDF files or the text raw text files, we needed to clean up, needed to extract specific sessions to make it a readable format to be processed by the NLP pipeline. On the NLP pipeline here, we show an example of how it comes out. This is in A lab, showing the entities extracted and also the relations between them. In the next slide, we'll have to have this scaled up. We have ASIF here to make this scaled up utilizing Microsoft Azure system, including the Azure SQL pool for the database and the Spark pools to build pipelines and notebooks, and the data lake storage for the file to store which is files. And if you have specific questions, ASIF can answer you this. Next, we have a little bit detail on the NERs, entity recognition. And in this part, we pick, you can hear we pick about 23 entities, including 4 major groups decided by 2 major sources. One is a trial, open cancer trials eligibility. The other is from the clinical researchers, oncologists. See the groups of the entities, including cancer diagnosis, including the stage and the metastatics and histology, cancer histology, also tumor grade, tumor size, and biomarkers, biomarker readout, pathology readout, and therapies, including the drug therapy, the surgeries, and medication, radiotherapies, and we also include the line of therapies. Another thing is the response to therapy, which from this matrix you can see most of them are the F1 score is good, is above 0.9, and some of them is not suboptimal. One of them is response to therapy. Response therapy including, for example, whether there is a recurrent, distant recurrent, local, regional recurrence, and whether the patient is responding, partially responding or completely responding to the current treatment. And this gives us opportunity to further improve this. We can mention this later. Next slide is about the relations. To get the relation, extract relation is more challenging than the named entity recognition. Here, thankfully, we have John Snow Lab to support us. We used half dozen different pre-trained models, relation models, including here you see the locational relations. There's the anatomic site and with others, and the temporal relations, biomarker without pathology, oncology, and we decided on the extracted here is about 25 types of relations based on 19 entities of priority to us. And to evaluate the performance of the relation extraction, we use we're not using the A lab. We use a different way. We decided to do not penalize the one's relation mistake because of the NER, because NER have separate assessment. So here, based on the relation evaluation on the diamond ones, so we have average F1 score about 0.9, which is pretty good. Next is we will use all of this data, this NLP data, integrated into a data model, which is actionable. I pass this to Scott.
Yeah, so to reiterate what Zach was saying, we chose specific data elements that we knew are poorly represented in structured data, but we knew we need them in order to study our patient population, either for biopharma-facing market access projects, for medical real-world data studies, or to give insights back to our partner networks, such as clinical trial matching that we'll get to in the future. We'll go on to show the demonstrable impact that the NLP pipeline had on enriching our structured data. So this is just an excerpt from the data dictionary that we've developed, 15 core tables, about 300 data elements, and rapidly growing, initially inspired by OMOP, but customized to our specifications. The whole pipeline updates nightly, of course, and the Azure system that Zach described is in continuous deployment, running over hundreds of thousands of patients and millions of notes weekly or nightly. And you can see a rather satisfying bump in some selected data elements. So we get about 68% increase in histology if we pull data from notes and incorporate it into the data model. Staging is up to about 20%. Presence of metastasis and metastatic sites about 40%. So definitely a clear impact on seemingly quite basic things like diagnosis, staging, metastasis. And biomarkers are, of course, increased a lot as well, because these crucial results are often found in PDFs and scans and not captured in structured fields. So we take this model and we go on to demonstrate a real-world application of how this NLP enhancement system can actually be a benefit to the networks and the patients. So shifting gears slightly, academic medical centers run a lot of clinical trials, and the community oncology patients also want access to analogous clinical trials, but enrollment is much lower. Often only a handful of percent of community oncology patients are enrolled in active clinical trials. So the question posed to us is, how do we identify patients that might be good candidates for open clinical trials? And it's actually an incredibly hard question. Oncology trials are growing in number and in complexity. They're mostly housed on clinicaltrials.gov, and that information's freely available. The problem is the crucial inclusion and exclusion criteria are in a kind of unstructured text blob that uses inconsistent language across different trial designs. So for example, one trial will call it colorectal cancer, another trial will call it colon cancer, another trial will call it CRC. So there's a lot of data cleaning that's necessary to even get a list of criteria with which you can match your patients to. And some of you are probably aware of these, quote, pure large language model approaches that are beginning to appear in the literature, such as Trials GPT that was published recently in a very impressive body of work. But going the pure LLM route, we considered computational cost, given the huge number of patients that we're dealing with, how to integrate structured fields if available, and how do you control for hallucinations, which is certainly a hot topic in the LLM space right now. So we opted for our, quote, AI-enhanced data model as the engine to match our patients to our trials. We do, however, make use of a large language model to extract criteria at scale for open clinical trials, and Zach will talk a bit more about the technical details there. So long story short, Any given trial has a set of inclusion and exclusion criteria. We have to extract those criteria, harmonize them to our data model, make sure all of the field names are consistent and line up. We do the same operation with our patients. We can then build a query based on the inclusion and exclusion criteria, and that produces a patient list that a trials coordinator can then review and decide if a given patient really is suitable for that clinical trial. Here's just a quick screenshot of the system that we've developed, our clinical trials app. So we've got filters on the left that the user can set up, an attrition plot to see where patients fall away from the trial criteria, where they are on a map, some demographic information, and we've also got, from our large language model pipeline, about 1,000 trials pre-populated with inclusion exclusion criteria that our clinical trials coordinators can easily access. So Zach's going to talk about the LLM criteria extraction workflow.
Yeah, because there are thousands of currently open cancer trials, and the researchers might want to save time to have it pre-built in the CT app we mentioned above. And here, again, we leverage the NLP integrated data model in our database. And the eligibility text is from the clinical trials gov website or database. So first step, we were using the OpenAI large language model to extract criteria, including whether the criteria is inclusion, exclusion, and what entities is, for example, would be a cancer stage, and what the value limitation it is, for example, is 3 or 4, and the logics between different criteria, for example, stage 3 or 3 above, and have a biomarker EGFR positive, and the lab test, for example. The next step is we found that there are dozens of criteria, and many criteria are not addressable or useful. So we built a machine learning classifier to identify those criteria we can be addressed using real world data, and then post-processing to clean and transform data into a format that could be used to pre-populate the filters. About the useful, whether it's useful or addressable, I have a few examples here. For example, life expectancy, and this one, every time we try to access this might be different, and the patient must have something, and those are not sometimes available from the database. Next, I'll show you some of the examples, some of the criteria extracted, how they are distributed between the sampled cancer trials. This is a summary from about 500 open cancer trials. The bars here, the blue means is inclusion, red means exclusion criteria, and the y-axis is criteria. It might not be readable to you, but I can point to you that in the bottom you see almost every trial have age and some lab test as an inclusion. In the red block here is as an inclusion. The exclusion, many trials have previous drug treatment, also have the comorbidities as an exclusion. And above there is a lot of biomarkers. Many trials have biomarkers as either inclusion or exclusion. And for each, to evaluate the performance of this, so we sampled 15 trials from top 5 cancer types listed here. And the expert, which is have MD degree, and experience with clinical trials, they try to give whether it's false positive, false negative based on each one we extracted. The the result here is the F1 score is above 0.8. This is we're just starting this. This can be first improved later. Yeah,
and
next.
I can talk about the performance. So to reiterate, this large language model pipeline opened our eyes to the power of these approaches. At a first pass, these numbers are pretty decent, but certainly not perfect. So we use them as a starting point for what the inclusion and exclusion criteria could be. So here's an example trial where we ran a head-to-head comparison with our clinical trial matching solution versus a highly used competitor software, which I will not name. We ran the analysis on the same day. It was around the Elaine 3 breast cancer trial. And we show that our system finds a greater proportion of eligible patients without such a high number of false positive patients that turn out to really not be eligible. Further analysis showed that our higher match rate was largely driven by the NLP enhanced biomarker and staging data that I mentioned earlier. This, of course, is just one trial, but we've repeated this story over 4 additional trials in recent weeks. And generally, the performance is looking really good and superior to some of the other solutions out there. And of course, this is good for patients. It means that our networks can more ably match patients to clinical trials and potentially enroll them, giving them access to new therapies where perhaps they've run out of options. So the final section of our talk, we're going to talk about next generation approaches. So much of our data is about continuous deployment of a natural language processing pipeline, but everybody's aware of the 2024 inflection point where large language models came to prevalence. We see that they're easy to work with. We put some effort into understanding them. And Zach led a project to build a hybrid NLP LLM approach to help us out with adverse events. So for those that don't know, an adverse event is essentially a bad reaction to a drug. You can see it here. So carboplatin, Taxol, Keytruda caused fatigue. So we've got entities and then a relationship between those entities and the adverse event. Problem is that the language used to describe these adverse events is so diverse that NLP often falls down. As a result, Zach came up with the following.
Yeah, we use a hybrid pipeline. Start with the NER, use John Snow Labs pre-trained model. We have for the adverse events, we have a BioBERT-based pre-trained model to get the NER. And then we apply the assertion assignment, use our trained model. And then for each sentence with a positive adverse events, so we will get it extracted together with flunking pair of sentences and use that as the input for large language model. We use a locally deployed large language model to comply for the privacy. And basically, for the large language model, basically asks 3 questions. One is whether there is adverse events. 2 is whether there is a treating cancer drug there. 3, whether there is actually association between each pair of drug and adverse events. And by this way, we're trying to leveraging the best of both worlds, right? For the NLP, we have a robust pre-trained NER models, and we already have it scaled up, and the running performance is much better. For the large language model, it's kind of more tolerance. We found more tolerance for the abbreviations, especially drug combinations and typos, and some drugs drug or advertisements we never seen in the trained model. It have better reasoning to get the positive relations, because some relations are not, there's drug are not it's negative related basically. I will show 2 examples here. One we call it true negative relation. The other one is true positive relation. Those are the true negative relation means the larger model do not detect this, and the annotator think they should not be detected. Here, for example, crizotinib and the diarrhea and shortness breath, because the patient is tolerant with the crizotinib, that the annotator think this is really, we should not report this. And true positive is alectinib here with bradycardia, because it's a worsen. I think this is true positive. And I would mention that the prompt engineering has been done by an actual oncologist with deep experience with AI, and annotator with MD degree. So this based on the annotation of about 140 sampled sentence groups like this, we got the F1 score above 0.9, which is promising. So we are scaling this up to all the patient knows.
Yeah, and of course, this could be very labor saving on our abstraction team. If we can achieve this accuracy or greater, then we can put less effort into manual chart review and more into insight generation. So that's all the data that we wanted to present. So we'll end with a brief summary and discussion. So we developed, validated, and deployed at scale a custom oncology-focused NLP pipeline using some of the tooling from John Snow Labs. We demonstrate the utility of this AI-enhanced data model in matching community oncology patients to open clinical trials. And we also show that in the future, perhaps NLP or LLM approaches used in hybrid can give us the best of both worlds in terms of computational scalability and accuracy. More futuristically, we begin to wonder to what extent will large language models replace these, quote, traditional ETL, extraction, transformation, and loading workflows that we've had for years. Is it that just a large language model can parse patient notes and then achieve greater accuracy once compute costs come down to a manageable level? We've already seen that the entire tool stack has rapidly evolved in this space, and everybody's working very hard to catch up. I don't know if we're there yet, and I think our approach, using smartly tools in the right context, thinking about prompts, thinking about base models, and always thinking about a rigorous evaluation is the way forward for the foreseeable future. So with that, I will say thank you, and Zach and I will sign off. We're very grateful for you joining, and we'll wish you a pleasant afternoon.
Yeah, thanks. Bye.